All right, so continuing on with 19.2, let's look at a more detailed look at resistors. So we really want to understand exactly what resistance is. So we can see from our studies on resistance thus far that both material properties and geometry impact the effectiveness. So if we have a, say, wire, we can see that that length times the area, so giving us the volume, would impact resistance, and that would impact the delta V across it. So let's consider delta V of a wire, and we're going to do steady state current. So we've got a wire, so we know E has the same magnitude everywhere. Thus, delta V, which we can find with that little integral that we've talked about before, from initial to final, E dot dl gives us delta V is equal to EL. And if we think about this in terms of current density, so J is equal to I over A for all cross-sectional area. And if we recall, uniform E means uniform V means uniform J. So all we're doing right now is just bringing together all of these concepts that we've been learning to understand circuits. So all of these three things are uniform across this section of wire with some resistance. And we also recall that J, current density, is equal to sigma, conductivity, times the electric field. And we might want to ask, can we write I, conventional current, in terms of conductivity, sigma, and delta V? Well, current density is sigma times E, and we can use E is equal to delta V over all L, and J is equal to I over A. And so we get that I over A is equal to sigma delta V over L. And so we can also write that I is equal to delta V over L over sigma A, which is equal to delta V over R. That famous circuit equation. But now we see how it all comes together by really understanding the material properties. In this case, R is resistance. And the units of R are volts per amps or ohms. And we can define resistance as L over sigma A. So we have the length of the resistor, the cross-sectional area, and conductivity. All defining the properties of that particular resistor. And this is what I mean by non-fundamental, because something like shape can actually change it so much. So, moving on, resistance depends on conductivity, which is the charge carrier, times the number density times the mobility of the charge, and geometry, length, and area, which is of course just volume. So let's think about the different ways that you could increase resistance. So you could use a material choice. You could use a material that's going to be more resistant. You could make it longer, smaller area. So all of those things will could increase your resistance. All right, so another way to express resistivity is using, and you'll see this expression a lot in other textbooks, so rho is equal to 1 over sigma. And with this expression, then R is equal to rho L over A. So just be aware that this is just another way of expressing resistivity if you see that elsewhere. We can also say I is equal to delta V over R, and thus delta V is equal to Ri, which is, of course, the equations that if you've done circuit work before, you should be very familiar with. All right, so let's look at what we have done so far. So we have done this primarily microscopically, and then we have just brought it into the macroscopic. And so let's see how this equation looks microscopically. So we think about currents in terms of electron flow. And we recall that the electron drift speed is equal to U times E, and I is equal to Q NA V bar, which is equal to Q NA U E. All right, so let's say delta V is positive. Thus, delta V is equal to EL for a straight wire. And so the electric field is equal to delta V over L. So then we can use this into our microscopic expression of current. I is equal to Q NA U delta V over L, which is equal to delta V over L over Q NA U, where this is, of course, resistance. So, and the purpose of this exercise is so that when you're thinking about these circuits, it's not just V is equal to IR. Well, that's true. There is some actually more interesting physics going on behind that. And that conceptual understanding of circuits is not only useful for having a more accurate picture in your mind, but it's useful for analyzing different types of situations. So when in doubt, go back to the basic fundamentals. All right, so we're going to move on, and we're going to talk about just some applications. On microscopic and the macroscopic measurements. So as I said before, making microscopic measurements is very difficult. Macroscopic measurements are easy. So for example, a voltmeter, ammeter, and an ohm meter. These are all macroscopic measurements. And you could use the macroscopic measurements with these equations to then derive what's happening at an elemental particle level. So, and of course, a microscopic expression would be V bar equals UE, and electron current NA V bar is equal to NAUE. And macroscopic, J is equal to sigma E, and I is equal to QNA V bar, which is equal to 1 over R delta V. Okay, so I want to go through a couple conventions that are in your book and introduce you to some conventions you might see elsewhere. So you'll typically see this expression as V is equal to IR in other books. But in this book, we use that delta V is equal to IR to clarify that this is a potential difference. Further, you might also see delta V, if it's coming from a battery, you might see this as EMF, and EMF is sometimes also written with a curly E. So just know that these are all just different symbols for the same thing. There's just a lot of different conventions within electrical expressions. Okay, so let's think about ohmic and non-ohmic materials. Get a little bit into materials science. So just note U, which is mobility, varies with temperature. So because of this, then conductivity, which is Q and U, and therefore resistance, which is L over conductivity times A, also depend on temperature. So whenever you're looking for these values, if you're looking at a precise table, you're going to see the temperatures that go along with it. And for the materials that, especially in a class like this, you're working with, conductivity is nearly constant, regardless of I going through. So for some, it's nearly constant. And for these materials, these are ohmic materials, which you can see why that might be kind of useful for the equations. So these are the materials used for resistors. So in equations, I is equal to delta V over R, where R is equal to L over sigma A, then this will be constant enough regardless of I. And obviously a commercial resistor would be made out of this type of material because they need to be predictable. So for a commercial resistor, if you doubled the length, then you would get twice the resistance and 1/2 the current. For delta V is equal to constant. And for a commercial resistor, if you doubled the area, then you'd have 1/2 the resistance and twice the current. For delta V is equal to constant. All right, so there is a type of material that's really interesting. And so these are called semiconductors. They've been one of the great discoveries of the last century. So let's look at the relationship between current and delta V for different metals, or for different materials. So we'll look at a metal. So you have I and delta V. And for this, the electrons are unbound the whole time. And if we look at delta V is equal to IR, we see there's a nice one-to-one relationship. And so as current goes up, so does delta V, or really more, as delta V goes up, current goes correspondingly. So this is how a metal behaves. So really, once you just get just a little bit of delta V, it gets going. Now, let's look at a material with bound electrons. So for something like this, a field could be needed to free the electrons. And once they're free, they'll be able to move. So in a case like that, if we look at I versus delta V, you'll increase and increase and increase delta V until you hit a particular threshold. And then all of a sudden, the electrons become unbound, and now you can have current. So field strong enough, really more here, to free electrons. So unlike a metal where you basically just need a little bit of delta V, current goes, here you need to ramp and ramp and ramp it up until you get to the point where the electrons can become loosed from their atoms. So, and then we have semiconductors. So these borrow on that principle that we just saw, where you have a material that requires a field, but they do something even more interesting. So with a semiconductor, the conductivity is equal to ENU, and U has an exponential dependence on voltage. So in a case like this, switch to my colors, you'll still have that threshold voltage, and then once you hit it, then the current goes up exponentially. Which you can think that can be pretty useful. So not just any voltage will set it up, but once you hit it, then all of a sudden you get lots and lots of current very, very, very quickly. So these are very, very useful and practical, and that's really the concept behind how they work. Okay, so going back to thinking about basic circuit setup, so non-ohmic circuit elements. So typically resistors are ohmic. But not always. It depends on temperature. So get your circuit too cold, all bets could be off. Your resistors could stop resisting. Capacitors are not ohmic. And from here, remember the voltage on a capacitor is proportional to Q, not current, so it can't be ohmic. So if you recall, delta V is equal to Q over C. And also, batteries are not ohmic. If you double the current through a battery, delta V will not change. So of course, the takeaway, if you're going to use I is equal to delta V over R, you better have an ohmic resistor. This does not work for all circuits. So that's what I mean by it's not a fundamental principle.